In this video we're going to derive the Euler-Lagrange equation using an analytic derivation. Now this is a derivation that Lagrange first produced. So we were used to seeing from the previous videos when we derived the Euler-Lagrange that if we had some extremum, now in this case here we've got some function y of x equals an extremum. So the example that we had before was a hanging rope, and the thing that that we produce an extremum on would be the gravitational potential energy. And in the case for a hanging rope, the extremum was a minimum. So we've got this extremum here, y of x, and what we did before is we changed the position of the rope in that example, and we looked at the change in position and the change in gradient, and we derived the Euler-Lagrange equation from that. But Lagrange came up with a different method. Rather than making the variation at a single point in a function, he made the variation over the entire function. So how did he do that? So what he did was he said, let's imagine we created a whole new function, we'll call it eta of x, and that's it in blue, and we said that eta of x equals 0 at these endpoints a and b. And then we were to multiply that eta of x by some number, epsilon. So epsilon is just simply a number. So that would give us a family of these little curves, and they would all stop at A and also at B. And then if you were to add this y of x and add on the variation here, epsilon eta of x, then you would get this function large y of x, which is in pink here. So you can see that we've this y of x, large y of x and small y of x, they're two different functions. Small y of x is the extremum, and large y of x is the extremum plus some variation. Okay. Another thing to note is that the value of eta at a equals the value of eta at b equals 0. And also the derivative of eta a and derivative of eta b equals 0, because outside here we just get 0, out here, out here. Okay, so the gradient at that point there is then defined to be 0. Another thing is that as epsilon here tends towards 0, then this value y of x is going to tend towards small y of x. In fact, whenever epsilon actually equals 0, the large y of x will actually equal the small y of x, really meaning that this curve here, the pink curve, tends towards the yellow curve as epsilon tends to 0. So if we write out our functional is this form here, i's integral from a to b of a function of x, y derived by dx. So this function y of x is an extremum, which means it ensures that the value y of x ensures that the value I is an extremum. So in the example of the hanging rope, it ensures that the value of the gravitational potential energy is an extremum. In that example, it happens to be a minimum. But what happens whenever we add on this variation here? Well, when we add on the variation, the function here changes. So if that function changes, then that value of I must change. So by adding on that variation there, the value of I changes. So I changes by some small amount, delta I. So you can then say that I plus delta I, the new value, is going to be the integral from a to b of the function of x times large y derivative. Okay, so we're just adding the variation on, where that y of x is equal to small y of x plus epsilon eta of x, and large y derivative of x is y derivative of x times epsilon eta derivative of x. So now what we're saying is, if we were to vary epsilon, the value of I changes. So I is a function of epsilon. We also know that whenever epsilon equals 0, the value of I tends towards an extremum. So we'll draw the three possibilities for the extremum out here. Either I is a minimum, in which case for all other values of epsilon, I is a larger value, or the value of I is a maximum, in which case for all other values of epsilon, the value of I will be less than that. Now the other option is it's an inflection point, so it can be inflected this way or it can be inflected that way. So it means that the value for I is going, it could be either greater or less, okay? So it's not a minimum or a maximum. But one thing that's common to all three is that at that point when epsilon equals 0, the gradient is equal to 0. Okay, so really what we're saying in words is the rate of the change of I with respect to epsilon, whenever epsilon equals 0, is just equal to 0. So in mathematical terms, we write that down. We're really just saying that the rate of change of I with respect to epsilon is just di by d epsilon. Whenever epsilon equals 0, there's an example, epsilon equals 0 is actually equal to 0. So let's go ahead, and we want to go ahead and compute this derivative here. So when we write it down, it's going to be d by d epsilon of this value I. Now we have to be careful here, because what is I? Well, I is not this thing here. The I is this thing here. Okay, because this I here, it only gives us one value for the I. So we know that y of x here is the function that ensures that this here is an extremal, meaning that it gives us this value here, and it's either a minimum or a maximum, or either, but either way the gradient there is equal to 0. Okay, but in order to not just look at that point there, but to look at every other point on this I-axis, we have to vary the value of epsilon. If we don't vary epsilon, we don't get any of this information out with here. We only get this one little bit of information at this point, at that point, and at that point. We want all the other information, so we have to vary epsilon. So in order to vary epsilon, we have to change this y to y of x plus epsilon eta of x. So whenever we're doing this differentiation, we've got to differentiate the x large y derivative. Okay, so we're going to differentiate that, and if whenever that equals 0, we'll know we have an extremum. But the question here now is, and this I'm going to get in a bit more detail than you might normally, the question is, how do we do this? So we'll work it out slowly and just work it out mathematically, a bit of logic. So we know that this value x here is not a function of epsilon. Okay, so x is just your real number line, and your real number line is independent of epsilon. Okay, no change in epsilon is going to change the value of your real number line. Now y here is a function of epsilon. We know that y is equal to y of x plus epsilon eta of x, and also y derivative is a function of epsilon, so y derivative equals y derivative of x plus epsilon eta derivative of x. So we can write this out, and I've put it in a little blue box for us. We can say that f is a function only of y and y derivative. Now you might say, well, it is actually a function of x as well, but it's a function of x implicitly, meaning as x changes, the value, as x varies, the value of we generate the entire term y of x. Okay, so it's only implicitly dependent on x. There's no explicit dependence. Plus, really, what we're dealing with here is we're going to be differentiating with respect to epsilon, so we're only really interested in the dependence on epsilon, and x has got no dependence on epsilon. Okay, so we've got f as a function of y and y derivative, but y is also some function of y of x and epsilon eta of x, and y derivative is a function of y derivative of x plus epsilon eta derivative of x. So generally what we can write down is, we can say that we've got some z as a function of y and y derivative. We can say that y then is some function g of Now, what is a function of? Well, it's a function of, we know it's a function of epsilon because we can vary that, but it's also a function of y of x. It's also a function of eta of x. So we can put y and eta, and the same can be said for y derivative. Now, the thing about this here is that this value y of x, well, that's the extremum. There only is one extremum. Okay, that's the function that ensures the functional is equal to a minimum or a maximum. So that once we know that y of x, it's fixed throughout the rest. So in effect, it looks like a constant. Okay. Now the same thing here with this value of eta. Eta is the function that we choose in order to create the variation. But once we choose that function, it remains fixed. And the same goes for the y derivative and the eta derivative. So let's go through and we'll go through this differentiation. So we're trying to find dz by d epsilon. In order to find dz by d epsilon, it's the same as df by d epsilon. So what we have to do, we have to differentiate f with respect to y, but then y is also a function of epsilon, so you need to use the chain rule. So f is a function of y and y is a function of epsilon. So we differentiate f with respect to y, but in order to do that we have to hold y derivative constant. So we have to use a partial differential. So we differentiate partial f by partial y where y derivative is constant, and then we have to differentiate y with respect to epsilon. But when we differentiate y with respect to epsilon, that's a partial differential as well, because we're assuming that the y of x and the eta of x are constant. Now, you might not be used to seeing it in this format because you'd be used to doing a differential, and the thing you would hold constant would be just say a real number line. But now here, the thing that's held constant isn't the real number line. The things that are held constant are functions. And you might ask the question, is it reasonable to write this and have the functions here as opposed to just normal variables? And the answer to this is yes, because in the end everything gets integrated and we just produce a number. So this value of y of x, if we were to have a different value of y of x, whenever it gets integrated we would have simply a different number. The same for eta of x, we'd simply have a different number. So in the end it all just goes back to through the integration sign goes back to a number. So we can write this here, and we can have these functions here as opposed to variables, and the functions are constant. We know the functions are constant anyway because one's an extremum as I've mentioned and it remains fixed, and the other one is the value of the function we use to create the variation, which whenever we pick it is fixed. Okay, now we do the same here with the second term here. So if we differentiate the function with respect to y derivative, we've got to keep y constant, and then when we differentiate y derivative with respect to epsilon, the y derivative and eta derivative are the terms that are constant within this partial differential. So a bit more detail you maybe see normally in this section, but I think it's useful to go over it. If we have a function here, this is a function here, I is integral from a to b of a function of x. Now this whole term here is our y, this whole term here is our y derivative. So we've done most of the work here already in the last section. So we're differentiating that with respect to I, and we've seen from above that's going to give us this term here. So it's exactly what we just worked out above. Now what we can do is we can simplify this again, because this thing here and this thing here, we can actually work out the differentiation for that. So partial y by partial epsilon, when your function y and eta are constant, equals partial by partial epsilon of this function here. Okay, so that there is your large y of x. Now whenever we differentiate this, we're going to differentiate the first term, so it'll be partial y of x by partial epsilon. Now, x is not a function of epsilon, so y of x is not a function of epsilon, so that whole thing is 0. Now, the second term here, we're going to use a product rule for differentiation. So we're going to differentiate partial epsilon by partial epsilon, multiply it by eta x, and then we're going to take epsilon, and then we're differentiating partial eta x by partial epsilon. Now, this term here, partial epsilon by partial epsilon, is going to be 1, so we're just going to end up with eta x. And this thing here is the same as the previous one, is that x is not a function of epsilon, so eta x is not a function of epsilon, so it means that this whole term here goes to 0, so you're just left with your eta of x. So it means that partial y by partial epsilon is equal to eta of x. Now, the same thing can be done for y derivative. I won't read through it, it's just the exact same as above, and you have partial y derivative of partial epsilon equals eta derivative of x. So now we can write that we can replace our eta, we can replace these terms here with our eta and our eta derivative. So I've just done that down there. So we have partial f by partial y eta of x plus partial f by partial y derivative eta derivative of x all by dx. Now, thing to note here, whenever we take this differential here, we're taking the limit as epsilon tends to 0. So as epsilon tends to 0, we know that our y of x, large y of x tends to small y of x, and our y derivative of x tends to small y derivative of x. Now, we've seen that before up at the top. As epsilon tends towards 0, this variation here tends towards the original extremal function here. Okay, so the y of x tends towards small y of x. Okay, so that's the point where you usually get to. Now, if you've seen the Euler-Lagrange equation before, done like this, you're going to use integration by parts, and it's the point where people kind of either give up or have a large sigh and just decide, well, just to accept the equation. So we're going to ask the question, we're going to do integration by parts, and we're going to say why we're going to do integration by parts. Well, we know that if this function here equals 0, then the value of I is an extremal. Now I'll head on to the next page there, and we'll finish this off just in a couple of minutes. So I've just rewrote that there. So if this thing is equal to 0, then we know that I is an extremum. So we've got one term here and a second term here. So for this to be true, that is that whole thing there equals 0, there must be something within that bracket there that must make that integral equal to 0. But we know that the eta of x doesn't equal 0. Eta of x is our function we use to create a small variation. If eta of x equaled 0, we would just be back to our extremum and we wouldn't be anywhere. Okay, the last 5 minutes we just wouldn't have happened. Okay, so if we can separate out this eta of x, and this is the point about integration by parts here, if we can take this eta of x out of that bracket there, then we can say what is left in that bracket must be equal to 0. So the question is then, how can we take the eta of x out of this bracket? We can take that eta there out, and it's straightforward, just take it out. But they've got an eta derivative of x here. So how are we going to handle that? So the question to that is that we want to actually turn that eta derivative of x into eta of x. And how are we going to do that? The $64 million question. And the answer correctly, you've answered correctly, it's we're going to use integration by parts. Okay, I just wrote IBP and shortened it. So just to be clear on this, we're going to end up with an integral from a to b of some function eta and something that's going to be left over. Now, the thing that's going to be left over is going to have to be equal to 0 in order to make this whole thing 0. Now, we can prove that by the fundamental lemma of calculus of variations, which we'll show you in the next video, but it's really just this statement here. Okay, and we're just really noting that this thing that's left over equals 0, and we're trying to find that thing that's left over. Now, we're going to use integration by parts on the second part of this thing here to try and get rid of this derivative sign. So I'll just go ahead and do that. Now, if you haven't seen much integration by parts, maybe get a wee book and have a wee read in it. So I'm not going to go through the details of how to do integration by parts, but I'll make a wee note of it here. So we're going to do integration by parts on this. So by integration by parts, it's written down if you had the integral of a product of two functions, so the integral of u dot v would equal u times v minus the integral of v du. So we let v derivative equal our eta of x. So then we can say that if we were to integrate this here, we would just have v would equal eta x. If we let u equal partial f by partial y derivative, so it means that the value du, well, we're differentiating the whole thing with respect to x. Okay, so it's got to be d by dx of u. What is u? Is partial f by partial y derivative. So then we put that into the equation above. We say u times v. So what is u times v? Well, the u times v is going to be our u is partial f by partial y derivative times our value for v, which is going to be our eta of x. I've actually put that down. It should be eta of x. Okay, so it's going to be u times v, which is our eta of x, and minus the integral from a to b of our function v du. So our v is eta of x and du is d by dx partial f by partial y derivative. Now we know that the value of eta at a equals the value of eta at b. Okay, that's just a statement that the crossover points is going to be the end points is going to be 0. Okay, as we've seen in the variational curve. Okay, so that's just these points here. They're going to be equal to 0. It was stated in the first page. So what we're going to be left with is we notice that if these points here are equal to 0, then this eta at a and eta at b is going to be equal to 0. So that whole term there is going to be 0. So you're just going to end up with a 0 minus this thing here. Okay, so what we're going to do is we're going to put this back into our original equation up here. So we're keeping that the same, and we did the integration by parts on this. And integration by parts we've found out is going to be this here, so we just put this into the equation. So we have d by dx partial f by partial y derivative of eta of x. Okay, so you can see we've done our work here. We've now got our eta of x instead of eta derived of x, and our partial f by partial y derivative is going inside the differential equations here, and there's a negative sign. Okay, so that whole thing is going to equal to 0. So it means that we can take out eta of x as we wanted to. So now we can take eta of x out. We're left with this equation here, which is our Euler-Lagrange equation, partial f by partial y minus d by dx partial f by partial y derivative. Now we know that the eta of x does not equal 0. So the eta of x term here doesn't equal 0, the something else must equal 0. So the something else here is just the Euler-Lagrange equation, and that's our Euler-Lagrange equation which we were going to derive. Okay, so and here we go, there's Mr. Euler and there's Mr. Lagrange, a couple of fine looking fellows. So I've gone through that in a lot more detail than I would normally. I think there's a few points in it that tend not to be picked up in other derivations. Hopefully I haven't done it to death. Okay, so thank you for listening. In the next video we'll go over the fundamental lemma of calculus of variations. Okay, goodbye.